All right, welcome everyone to the July series for the Maths Extension 1 lecture here at A2 Notes. My name is Leo and I'm going to be your lecturer today. Thanks everyone for tuning in. And yeah, just before we begin, I want to quickly talk to you guys about A2 Notes, who we are. A2 Notes, we're an educational company and we're run by past students for students. And we've been around since 2007. We've been offering these free lectures for since 2015, and our goal, our ethos, is all about accessible education and helping you do the best you can in your high school studies. So to help you do that, we offer a bunch of free resources, which you can see on these slides here. We have a website with hundreds of study notes that you can download for all of your subjects. Obviously, we offer these free lectures during the holidays. And we also have a discussion board with a forum, and we got a YouTube channel with videos. We have newsletters and articles and just a whole bunch of resources that you can check out on our website. And if you explore this lecture page where you're watching this lecture, there should be links to our resources there. We also offer a few paid premium resources if you do need that extra support. We offer a tutoring program called TuteSmart, and as well as printed study guides and revision materials, and also a digital subscription service called Ed Unlimited, where you can access those study guides to access course notes, topic tests, and also your text guides for your English text as well. So yeah, with that said, let's just dive straight into the lecture. So welcome everyone again to the July lecture. And yeah, my name's Leo and I can't wait to get started. So yeah, again, thanks for tuning in. We have, during this live premiere of this lecture, we have a Q&A below. So I'll be actually monitoring your questions while this lecture live streams, live premieres, I should say, and I will be monitoring and answering your questions. So if you have any questions that pop up during this lecture, feel free to sort of pop them down below and I'll go ahead and answer them. And again, special thanks to our university sponsors, whose these lectures wouldn't be possible without their support. So shout out to them as well. So a little about who I am. So some of you may already know who I am if you've been to any of my previous lectures, but my name's Leo and I graduated high school in 2018. Wow, it's been a while since since high school, but yeah, I graduated back in 2018 and I did a weird mixture of subjects. I did biology, business studies, English advanced, 4-unit maths, and also modern history. So a mixture of subjects across the board, and I managed to get a band 6 across all of them. So that would I was on the Premier's all-rounder list for that. And I achieved an ATA of 99.45. And I think around like 187 people did Extension 1 at my school. For 187 students did Extension 1 maths, and I managed to come first out of all of them, which helped me get an overall mark of 99 for Extension 1 maths, because if you do Extension 2, you get a mark out of 100 instead of 50. So I'm currently studying a combined arts and law degree at the University of Sydney, which I'm really enjoying. Yeah, I'm almost done with that. I've got one more year to go after this year. And I'm also a massive Swiftie. So yeah, really excited for her to come to Australia next year in February with the Eras tour. It's really exciting. And yeah, I'm just a really big Swiftie. Shout out to my fellow Taylor Swift lovers. So I've been at A2 Notes and TuteSmart since 2019. So it's been a while. Yeah, before we used to have our lectures in person. I think some of them are being brought back in person, but yeah, for Extension 1, we have this sort of online lecture instead. Obviously, because of COVID and everything, it's sort of really impacted the way we've been delivering these lectures. But yeah, shout out to the in-person lectures back in 2019. And yeah, I actually wrote the Richard III text guide just for, yeah, because I studied that for my HSC. So if anyone is studying it, feel free to have a browse through the text guide there. So today's lecture is sort of split into two halves. So we have our first half, where we'll be sort of talking about Extension 1 and how we approach it as a subject. and also looking over the syllabus and making sure we are covering everything you need to know for trials. And also we'll be revising mathematical induction, extension 1 integration, and also volumes of solids of revolution. And the second section, sort of in this lecture, we'll be looking at vectors, including the higher concept material, including dot product and projections. We'll also be looking at the statistical analysis topic on the binomial distribution. And then we'll be wrapping up with tips, both to help you avoid losing marks, including specific advice for trigonometry and calculus, and also some final maths exam tips. So in the last lecture series in April, I covered a large chunk of the Maths Extension 1 calculus topic already, including differential equations. Since I covered it last time, I won't be covering it in as much detail in the July series right now, but you can actually access the recording here on that link. And of course, you have access to my slides, which are on this lecture page, so you will be able to sort of go through any of the sort of content that we don't get through today. So just sort of a current status where you guys are. So you guys are in the July holidays right now. You've got one more term to go, which is term 3, and then afterwards it's straight into HSC exams. So your timetable already came out, and we know that the Extension 1 Maths exam is scheduled to be on Friday, 20th of October. So this is less than 4 months away now. So to be exact, it's 3 months and 15 days. And you've already completed some assessments at school, so most of you guys have already done half yearlies, and the majority of you will be sitting your trials exams next term. So you'll be sitting like sort of full length HSC style exams in term 3. So what this lecture is aimed at, it's preparing you for trials. So we'll be doing a broad coverage of the course, and I'll be providing heaps of tips and tricks along the way. And just sort of a forward, there is a lot of content we do have to cover, so I'm not sure if we'll be able to get through everything today in these 2 hours. But again, you do have access to my slides, so you'll be able to sort of go over any material that we don't get through today. So at this point of the year, you are well and truly into the Extension 1 course, so you should already have a good grasp on the content of your syllabus. However, all the maths topics can get jumbled up easily in your head, sometimes because of the way that with Extension 1, usually you have like the same maths teacher, and you might be for both Maths Advanced or Maths Extension 2, depending on which one you're doing Extension 1 with. So sometimes it can be a bit confusing in terms of, oh my gosh, is this topic a Maths Advanced topic or is it Extension? Or if you do 4 unit, is it Extension 1 or is it Extension 2? Like, will I be tested on this in the Maths Extension exam? So it can be a bit sort of overwhelming in terms of the content. So that's why it's a pretty good idea to go over the syllabus before trials. So make sure so that's why we're going to be doing a syllabus overview, and make sure that you are on top of your syllabus. So I'm really sorry to tell you, but the old syllabus can't come to the phone right now. Why? Because it's dead. So just remember, you guys are sitting the new syllabus, which was first examined in 2020. So any past paper that you accessed before 2020 is actually on the old syllabus. So therefore, it's a good idea that you have a clear understanding of what is in the new syllabus, so you don't get surprised in the exam. So I know you probably heard this like a million times by now at this point of the year, but the syllabus is your best friend. It's cliche, but it's true. You kind of want to treat it like your best friend. You want to treat it like your Bible for the purpose of the HSC, because it tells you everything you need to know. And yes, I can't examine you on anything outside the syllabus. So you just want to treat the syllabus like your best friend. You want to know it like the back of your hand. And it's important to know what topics are new and what topics have been moved in the new syllabus, so that you are able to utilize past resources effectively. So, for example, in the old syllabus, we used to have projectile motion questions. We also had integration by substitution questions. So since you know that it's still in the new syllabus, you can still use those past papers for those specific questions. Whereas some topics like vectors or like statistical analysis, that wasn't in the old syllabus, so you won't be able to sort of test your knowledge on that using past papers. Also, just a warning to you guys, make sure you don't neglect year 11 content because they can be assessed as well in the exam. So up to, I think the guide is around 30% of the marks in the HSC paper come from year 11 content. So don't forget to study for year 11 content as well. It's really important. I think if you go to the 2020 HSC paper, I think a lot of the students, there was lots of controversy with that paper because I think the final question, question 14, had a lot of content from year 11 and people just were blown away by how much of an emphasis there was on year 11. So if you go to 2020, you'll be able to see just how important year 11 content is. So don't forget to study for year 11. So here is your syllabus. And we can sort of look over the year 11 and year 12 course. So in year 11, you looked at functions, trig functions, calculus, and combinatorics. And in year 12, you need to know proof. So proof of mathematical induction, you need vectors, you also need trig functions. We've got this big calculus topic, which is split into two subtopics, further calculus skills and also applications of calculus. And then we also have statistical analysis in year 12 as well. So I flagged here what I call Extension 1 standalone topics. So what I mean by this is we know that Maths Extension 1 is, in its name, an extension of Maths Advanced. So with all the other topics, they require sort of Maths Advanced knowledge. For example, in Extension 1 Calculus, you learn how to do integration by substitution, but that draws on and expands on your Maths Advanced knowledge of how to integrate in the first place. But with these blue Extension 1 standalone topics, that just means that they're sort of specific to Extension 1 in that they don't sort of build on any existing Maths Advanced content. So they're sort of Extension 1 exclusive. They don't really have any Maths Advanced sort of ties. And I've also put here with an asterisk, so new syllabus topics. So we know vectors and statistical analysis are completely new. Although that doesn't mean they're the only new areas. It's just these are just outright the entire topic new. There are also new areas to other topics as well. For example, combinatorics used to be in the old syllabus too, but in the new syllabus, you guys specifically have the pigeonhole principle that's been introduced. And also in applications of calculus, you guys have a new section on differential equations. So that wasn't in the old syllabus, but it's been added to the topic. So in summary, you need to make sure you're on top of 6 areas for your HSC exam. We have mathematical induction, vectors, trigonometry, calculus, statistical analysis, and year 11 content as well. So it's kind of like mastery over the 6 infinity stones. You kind of like collecting your infinity gauntlet and making sure you have all 6 infinity stones. So make sure you're on top of all these 6 areas with induction, vectors, trig, calculus, stats, and also your year 11 content too. So approaching Extension 1 Maths, like any maths subject, Extension 1 is skills-based. So you kind of want to study in 2 halves. You want to make sure you understand and also apply as well. So understanding is all about making sure you're on top of all the content and having a strong theoretical understanding of sort of the theory and the concepts in the course. But applying is making sure that you can actually take that knowledge you've understood and sort of apply it to a question. And you do that by sort of doing past papers and past questions, exposing yourself to all these different question types and making sure you have the ability to sort of use the skills that you learned and actually apply your knowledge of the course material to a question. So yeah, you kind of want to study in 2 halves. Extension 1 is unique because it is a subject which can either count for 1 unit or 2 units, depending on whether you pair it with Maths Advanced or Extension 2 Maths. So again, as I mentioned earlier, if you sort of do Extension 1 with Maths Advanced, you get a mark out of 50. But if you do it with Maths Extension 2, then you'll get a mark out of 100 because it'll count for 2 units. But unlike other subjects like studies of religion, where the paper sort of differs if you do just the 1 unit or the 2 unit version, in Extension 1, you will sit the exact same paper. And the way that extension works is there should be a bunch of standard questions. So usually a few questions you see, sort of the structure, the routine of solving those questions should be pretty familiar. But again, there will be a few curveballs as well in the paper. But the best thing about Extension 1 is that the questions never get too hard. As long as you are on top of your content, you will be rewarded for your efforts. Whereas Extension 2, from personal experience, is sort of, that's the course where they sort of throw in the really wacky questions, which require a lot of abstract and creative thinking. So in Extension 1, usually if you put in the time and effort, you will be rewarded. So this is what your exam paper will look like. So the Extension 1 paper is 2 hours long, which is 1 hour shorter than the Maths Advanced and Extension 2 papers, which will be 3 hours long. And instead of being out of 100, it will be out of 70, and you'll have 10 multiple choice questions, and then you'll have 4 questions, questions 11 to 14, consisting of multiple parts, which are each worth 15 marks. So there'll be like sub-questions underneath each question, and in the exam, I believe you will have separate writing booklets for each question. That's how it was like when I sat my HSC back in 2018. Whereas with Extension 2, you have 6 questions, questions 11 to 16, which also are worth 15 marks. Maths Advanced used to be the same, but in the new syllabus, they've sort of broken the structure, and instead they have a bunch of these questions, short answers, like a bunch of questions that don't follow the same sort of structure as it used to be like this. So just a quick discussion. Do you do the multiple choice questions first or last? That's a common question that I often get asked. Me personally, I always did the multiple choice questions first because I thought it was a good way to sort of ease myself into the exam and sort of get me into the headspace of doing maths. But I also have friends who I knew do the question, the multiple choice questions last. Their rationale is that you can always, if you're running out of time at the end, you can always guess the multiple choice questions, and you have like a 25% chance of getting the right answer. So they would save it last. But for me, I always did them first because I thought it was just a nice way to ease myself into the exam. But it's up to you and sort of do what works best for you. So how did I study for maths? So consistent effort for maths throughout the entire year meant less stress come exam time. So the best thing about maths is that it's a skills-based subject, not a content sort of heavy subject, unlike biology or business studies, for example, which means that if you have the skills to sort of tackle questions, then you don't really need to stress when it's exam time, because all you need to do is go into the exam room, sit, whatever question comes up, you just tackle solve the question, and it's like you don't need specific like dates or specific statistics or something like that you need to know, or like quotes for English, for example, which meant like just by putting consistent effort throughout the year, I made sure I built up my math skills, and that meant during exam time, I sort of studied the least for maths because I could dedicate my time towards my other subjects because I felt really confident with maths and I didn't need to stress about it. I also didn't use a reference sheet. So I was one of these people who never used a reference sheet, but I made sure I knew what was on it just in case I had like, I don't know, a mind blank in the exam or something and I needed to quickly refer to a formula. But I did so many practice questions, I already basically knew all the formulas by heart that I didn't need to use a reference sheet. And before exams, my routine for studying maths purely consisted of doing past papers because I feel like they're the best study resource for studying for maths because they sort of assess your ability to apply your skills and your knowledge in order to tackle questions. Obviously, you guys are on the new syllabus, so this isn't as much of a viable option for you guys because but you guys are sort of lucky in the sense that you aren't exactly the first people to sit the new syllabus. You've got the class of 2020, 21, and 22. So you guys have 30 sets of past papers at your disposal. Also the sample paper, so that's like a 4th past paper too. I also do recommend you attempt a range of questions from different sources. So your teachers at school are there to support you. So if you want extra questions or extra help, just ask your teachers and they'll be able to provide them for you. Also, I recommend doing like trial papers from other schools. There's like an awesome resource online called HSC that is, it's basically like a database with a compilation of past trial papers. So those, you can get your hands on those and you can have a bunch of extra past papers to do. And if you know which topics were in the old syllabus, you can also practice doing them on old past papers as well. So you can still use old past papers to help you study. And as I mentioned already, maths was the subject I dedicated the least time towards in the lead up to trials and the HSC because I just put consistent effort throughout the year and then I would dedicate my time towards my other subjects that required sort of more attention in the lead up to HSC, like for example, advanced English. So, okay, that's all about maths extension 1 in general and studying for it and approaching the subject. On that note, let's actually dive into the substantive revisional material today. So let's quickly look at mathematical induction. So remember that mathematical induction is your proof technique that you have in order to prove statements that are asserted by natural numbers. For example, if you have a statement like, oh, if we add up all the odd numbers up to 2n minus 1, that will be equal to n squared for all integers n is greater or equal to 1. And the way that mathematical induction works, I really recommend you understand it. Don't just sort of rote learn or like blindly memorize the steps without understanding why it works. It basically, the rationale behind how it functions is it's sort of like a domino chain. I like to visualize dominoes. It works by proving that if a statement is true, then it will be true for the one after it, thus creating a chain effect. So if you can prove that if true for a certain number, then the statement will be true for the next number. If you can just prove one base case, then by that sort of inductive logic, you'll be able to tip all those dominoes and then you'll be able to sort of prove it for all integers. So there are 3 main types of induction questions that we have in mathematical induction. We've got equality, we've got divisibility, and we also got inequality mathematical induction questions. And all 3 types were previously tested in the HSC for extension 1. However, because of the new syllabus, you guys don't need to worry about inequality type induction questions anymore because NASA was nice to you guys and moved them all to extension 2 because generally inequality ones were a bit harder than the other 2 types. Of course, if you do extension 2, you still need to worry about inequality type induction questions, but if you just do extension 1, you don't need to worry about them anymore, and you just need to focus on equality and divisibility type induction questions. So there are 4 main steps of any mathematical induction proof. It doesn't matter if it's divisibility, inequality, or it doesn't matter if it's equality, divisibility, or inequality. All of these 4 steps will stay true no matter what type of induction question you're doing. And the steps are that for the first step, you want to make sure you prove true for the first integer of the domain. So read the question. Usually this is n equals 1. However, sometimes it might start with a different integer. For example, I believe in a past paper for extension 1, in the last few years, I think it was last year's paper maybe, I can't remember which one it was specifically, but it started with n equals 0 in that year. So you just want to make sure you read the question carefully. Then step 2, you want to assume that the statement will be true for some general number, some general term n equals k. And then for your third step, you want to prove true for the general term n equals k plus 1 using the assumption from part 2. So that's really important that you use the assumption, because the whole basis of how induction works is that if true for a number, it will be true for the next number. So it sort of relies on the previous number being true. And then for your final step, you want to make sure you always remember to write a conclusion to sum up what is going on. So make sure you sort of finish your proof with a conclusion to wrap up your proof. So step 1 forms what we call the base element of the induction proof, and steps 2 and 3 form what we call the inductive element. So the reason why it's important to have both steps is because it's kind of like dominoes. Steps 2 and 3 ensures that all the dominoes are lined up nicely. So it's saying that if the domino before it falls, then the next domino will fall as well. That's basically what steps 2 and 3 say, that if true for a number, it'll be true for the next number. So basically saying if one domino falls, it'll tip over the next one. However, if you just have dominoes all lined up perfectly, that doesn't mean they fall yet. You need this first step, the base element. You need one domino to fall over to set off a chain reaction of the other dominoes falling as well. Because if you don't have that initial push, none of the dominoes will fall. So the steps 1 is making sure that at least one domino falls, so that it will trigger this chain reaction, and it will make the other dominoes fall as well. So you need both of them in order to satisfactorily prove something by mathematical induction. If you don't, you might end up with something called a false proof by mathematical induction, which is something the syllabus explicitly mentions you need to know about. It's been added to the new syllabus, and yeah, you've got to make sure you can identify errors in false proofs by induction. So for example, if you have a proof where steps 2 and 3 work out perfectly, but you haven't done step 1, that might be a false proof. And the reason why this is the case, again, as I explained, without the inductive element, the statement isn't true for every integer in the domain. So the dominoes logic hasn't been used or can't be applied. So for example, with 3n equals 6, this statement isn't true for all integers n is greater or equal to 2. It's only true for n equals 2. So you haven't like sort of shown that there's an inductive element there. However, if you don't have the base element, what you've done is you've proven that the statement is true for an integer if it is true for the integer before it, but you don't have the initial first step to set off that chain reaction. So for example, you can prove something will be true for n equals 2 if it is true for n equals 1, but if you haven't proven it's true for n equals 1, then you haven't proven it's true for n equals 2 either. All you've proven here is that it will be true for n equals 2 if it's true for n equals 1, but if you haven't proven it's true for n equals 1, that means you haven't proven it. That means it won't be, like, you haven't shown it's true for n equals 2, because the whole truthfulness of n equals 2 is conditional on the fact that n equals 1 is true. So basically, a too long didn't read. Just make sure you don't be lazy and skip any steps. Make sure you include all the steps always in an induction proof to avoid a false proof by mathematical induction. So there's also another area in this topic which is quite controversial, and that's sort of in step 4 about what sort of conclusion you should write. So we got short and long conclusions. So a short conclusion might be something like, by the principle of mathematical induction, the statement is true, or something like that. Whereas a long conclusion basically expresses what's going on in sort of a full like sort of explanation. So it's something like, if the statement is true for n equals k, it will be true for n equals k plus 1. Since it is true for n equals 1, it must be true for n equals 2 and n equals 3, and so on for all integers n is greater or equal to 1. So when I was in year 12, when I was in high school, my teachers only allowed us to write the long conclusion. They would not accept the short conclusion as well, because they said that it didn't illustrate that we understood what was happening and why induction works. So we would be penalized if we didn't write the long conclusion. So I always personally just wrote the long conclusion. However, if your teachers at school allow you to write the short conclusion, by all means, you can do that. Just do what your teachers tell you to do because they're the ones marking your assessments. But I've also put this sort of table here about the pros and cons of the different types of conclusions and why you might want to choose doing a short conclusion or a long conclusion. But yeah, I personally always just wrote the long conclusion, and it's not too much longer to write, and also it does strengthen your proof because it shows the marker you understand what is going on, and it also helps you to remember the actual induction steps because it's all reiterated here in the conclusion. You got your step 2 here with the assumption. We have our step 3 here, and we also have our base case here too. So, but yeah, it's up to you. Just make sure you're aware of what your school sort of your school's guidelines and sort of what they expect from you guys. So my tips for mathematical induction: make sure you always write a conclusion. Make sure you stick to the steps and work methodically. So keep in mind the 4 key steps and sort of follow that structure. And illustrate that structure clearly to strengthen your proof. Make sure you always use the assumption in your 3rd step that you make sure in step 3 you always use the assumption that you made in step 2. And when you're substituting values of k into n, make sure you're using brackets because a lot of the time errors can occur if you incorrectly substitute something into the statement. So make sure you're very careful when you're substituting numbers in. And at the beginning of step 3, you should write down a RTP, which stands for required to prove, to keep yourself on track and remind yourself what you want your end result to be. So we'll see what I mean by RTP when we do a practice question together. And for divisibility type induction questions, make sure you explicitly state that you are working with integers. So let's try a question together now. So this question is an E4 level question, which is slightly harder than the standard ones you see in past HSC papers. And you'll see why when we start doing it, because this induction question sort of requires some creativity in terms of how you solve it. But it's still an induction question and it still follows the 4 main steps that we talked about earlier. So we're asked to prove by mathematical induction that 34n cubed plus 206n is divisible by 12 for all integers n is greater or equal to 1. So let's go ahead and do this question now. So I'm going to start off with my first step. Oops. So remember, your first step is to prove true for the first integer of the domain. In this case, we're asked for all integers n is greater or equal to 1. So therefore, I'm going to prove true for n equals 1. Like so. So I've proved true. So that means I'm going to substitute 34 n equals 1 into the statement. So 34 times 1 cubed plus 206. 1 is going to be 34 plus 206, which will give me 240 when we add 34 to 206. So therefore, this is the same thing as 12 times 20. So therefore, it's going to be divisible by 12. So we can say therefore divisible by 12 and therefore true for n equals 1. Like so. So don't forget your base step. It's really important. Without it, your induction proof won't work because you need that initial push to set off the dominoes. Okay, so your second step is you want to assume true for n equals k. And remember, k is any integer that's greater or equal to 1. So we can just say k is just some general integer that's positive. So if you do extension 2, you might see this notation. This just means n is an element, is a member of the set of integers, so just fancy Z just means integers, the set of all integers. And when I put a little plus, it just means positive integers. But you can also write in words K is positive integer or something like that. But here I'm just going to use this shorthand. So I'm going to say that 34k cubed plus 206k is equal to, in order to express this as something divisible by 12, I'm going to write 12p. I can choose any letter I want, but the important thing is you can't forget this. You need to specify that p is an integer. Because if you don't, p could be a fraction, and then this wouldn't be divisible by 12 anymore. So you can choose any letter you want. I'm going to use p, and I'm going to say where p is an integer. Okay, so that was steps 1 and 2. My third step is going to be prove true for n equals k plus 1. So here's where I write my required to prove. So what am I trying to prove? I'm trying to show that 34k plus 1 cubed plus 206k plus 1 is, and here's what I mean by putting it in brackets. Make sure you are careful when you're substituting numbers into n. So this is going to be divisible by 12. So I'm going to say I'm required to prove that this is going to be 12 times another letter. Because I already used p, I'm just going to use a different letter. And I'm also going to specify that q is an integer. So now we can start beginning on our left-hand side and trying to work our way to the right-hand side to show that it's divisible by 12. So I'm going to say on the left-hand side that this is 34 k plus 1 cubed plus 206 times k plus 1. And now I can expand the brackets. So you can use your year 11 knowledge of binomial expansion with Pascal's triangle to expand this. So this will be k cubed plus 3k squared plus 3k plus 1 plus 206k plus 206. So this is going to be, when we expand, that's going to be 34k cubed plus 102k squared plus 102k plus 34 plus 206k plus 206. So this is what we have on the left-hand side now. Remember, in our third step, we always want to make sure we're using our assumption somewhere. So let's ask ourselves how we can use this assumption. So we know that 34k cubed plus 206k is 12p. So we have a 34k cubed here, and we also have a 206k here too. So what I'm going to, so because we assume this is true, we're going to assume this is going to be equal to 12 times some integer. So I'm going to replace it with that. So this is going to become 12p, these two times 34k cubed plus 206k, and then I have the rest of my expressions. So 102k squared plus 102k plus so 102k squared plus 102k plus 34 plus 206, which is 240. Using assumption. So I like to write it to flag to the marker that I've used the assumption and show that where that result came from. So now what I can do is try to take out a 12 in front of all of these terms to see if it's divisible by 12. So what happens if I factorize out the 12? I'll get p plus 102 divided by 12 is going to be 8.5 or 17 over 2. K squared plus 17 over 2k plus 20. When I do 240 divided by 12, yep, 20 like that. So normally this, you'll be panicking and you'll be wondering, oh my gosh, something went wrong. Because usually here, this will all be nice integers. And that's not a nice integer, that's a fraction. So you're probably panicking and you're like, oh my gosh, did we do something wrong here? And this is why this is an E4 level question. You have to be creative and think sort of carefully and outside the box. So in order for this to be divisible by 12, all of this stuff, all of these things inside the fraction, inside the brackets here, it needs to be equal to Q. It needs to be some integer. So we know P is an integer, we know 20 is an integer, but 17 over 2 is not an integer. But what we notice here is that I can actually factorize out a 17 over 2k from both of these terms, and let's just see what happens. So if I take out a 17 over 2k, this will give me k plus 1, like that. So when I factorize it, this will be 17 over 2, k times k plus 1 plus 20, like this. So now we need to do some justification, and we're going to look carefully at what's going on. We know from step 2 that we said that k is an integer. So this is an integer, and k plus 1 is also an integer. It's just going to be the consecutive integer after it. So we can say, but what happens when we consider consecutive integers? For example, if k was like, I don't know, 3, the next integer will be 4. And if we multiply it, this will be 12, which is an even number. But if this was like, I don't know, like 9, and this was 10, that would be 90, which is also divisible by 2. If this was like 6, and then that was 7, that would be 42, which is also divisible by 2. What's actually going on here is k can either be even or odd. So if it's even, that means k plus 1 will be odd. But when you multiply an even number with an odd number, it will always be even. But if k was odd to begin with, if we add 1 to it, it will be even. And an odd number times an even number is also an even number. So no matter what happens, the product of two consecutive integers will always be even. And if it's even, it's divisible by 2. So it will cancel out this 2 at the front, and it will be a nice integer. So it's divisible by 2, so the 17 over 2 doesn't matter. It will still result in an integer. So we can say k times k plus 1 is always even, but is even because product of two consecutive integers is always even, because odd times even is even, and even times odd is even. So you can justify that. And because of that, we know that we can say, if I'm running out of space here, but we can just say, therefore, 17 over 2 times k plus 1 is an integer. Because if k times k plus 1 is always even, it's divisible by 2, so it will result nicely into an integer. So therefore, this thing is equal to 12q, where q is equal to p plus 17 over 2k times k plus 1 plus 20. Because p is an integer and k is an integer, all of that. So therefore, it's equal to the right-hand side. So then afterwards, you will have to write a conclusion. So for me, I would, I'll just write it here, because I ran out of space over here. I'll just say, therefore, if true for n equals k, it will be true for n equals k plus 1. That's what we just did in steps 2 and 3. We basically said, assuming this is true, then this thing will also be true, and it did turn out to be true once we used the assumption. But in step 1, we showed that it was true for n equals 1. So we can say, since the statement is true for n equals 1, it will be true for n equals 2 and n equals 3 and so on for all integers n is greater or equal to 1. And there, ta-da, we just completed that mathematical induction proof. So yeah, you can see it's a bit harder than your usual ones. Not only did we have to use Pascal's triangle to expand that using your knowledge of binomial expansions, but also you had to think creatively here in order to illustrate why this thing is still an integer. Okay, so that was our revision on mathematical induction. Now we can sort of dive into calculus. So just another reminder that we won't be covering calculus in that much depth today because I did cover it in the April lecture series. So again, you can go revisit the recording from the last lecture series using that link there. So in extension 1 integration, you have specific areas, which are integration by substitution, as well as how to integrate sine squared x and cos squared x. So just with integration by substitution, remember to always convert back to the original variable if you're doing an indefinite integral. And if you are doing a definite integral, remember to change the limits. It's so easy to forget to do, and if you do forget to do it, you won't get the full marks. Also, in extension 1, if the question tells you to use a substitution, you have to remember to use the substitution. You must use it. And the beauty of extension 1 substitution questions is that the question will always give you the substitution. It will always tell you what to substitute. Whereas in extension 2, you might be asked to sort of come up with your own substitution. And they won't necessarily have it. So you might be able to, you'll have to sort of write down your own substitution. That's not going to happen in extension 1. However, if an integration question doesn't specify a substitution, you might also be able to do the integral by inspection without a formal substitution to save time. And that involves the use of the reverse chain rule. So here's some past extension 1 questions. So here they're like, use the substitution u equals 2x squared plus 1, or otherwise find this integral. And then here for 2004, use the substitution u equals x minus 3 to evaluate this integral. So here, in terms of the wording, they give you the substitution, but they said or otherwise, which means you don't have to use it. You're allowed to just do it by inspection with the reverse chain rule. Whereas here, they just say use it, so you must use it. So let's go and tackle these questions to sort of revise how to do integration by substitution. So here in the 2005 HSC, we're asked to use the substitution u equals 2x squared plus 1, or otherwise to find this integral. So remember, with any substitution question, when you're using it, you need to specify what you're letting u be equal to. So here it's going to be 2x squared plus 1. And then we're going to differentiate our substitution. So we can say du dx is going to be 4x. That's going to be our derivative. So therefore, we can say du is going to be 4x dx. So we can treat the derivative sort of like a fraction for the purpose of the HSC, and we can move the dx to the other side. And then what I'm going to do is I could divide by 4 on both sides. So du divided by 4 is equal to x dx. So now I have my original integral, which is x times 2x squared plus 1 to the power of 5 over 4 dx. And now I'm going to substitute all the variables and convert them all in terms of u. So we have an x dx here, which becomes a du over 4. And then we have a 2x squared plus 1, which is just u to the power of 5 over 4, like that. So this will become 1 over 4 integral of u to the power 5 over 4 du. So we can raise the power by 1. So 5 over 4 to the power of, when we add 1 to that, it will be 9 over 4. And we divide by the new power. So this will be 1 over 4 times 4 over 9 u to the power of 9 over 4, which will work out to be 1 over 9 u to the power of 9 over 4 plus c. So don't forget your plus c because this is an indefinite integral. However, if you leave the question like this, you won't get the full marks either because you need to remember this is just a substitution. We need to convert back to our original variable. So we said that u was 2x squared plus 1. So this thing will be 1 over 9 2x squared plus 1 to the power of 9 over 4 plus c. And that is your final answer. So yeah, that's how you would do it using the substitution. However, if you wanted to use, or otherwise, if you want it to be quick and just do it by inspection, you can just use the reverse chain rule here without needing to do the formal substitution. So I'm going to redo this question, but without using the substitution this time, just to illustrate how you can do it by inspection. So our integral is x times 2x squared plus 1 to the power 5 over 4 dx. Now here's the thing. This is a function, but there's a function within the function. So when we try to integrate a function that has a function inside, we want to make sure that the derivative of the function inside is on the outside before we can integrate it, so that we can use the reverse chain rule on it. So the derivative of 2x squared plus 1 is going to be 4x. That's what the derivative is. So I want to have a 4x on the outside. The problem is I don't have a 4 on the outside. I only have an x. So in order to get a 4x on the outside, I can just multiply by 4, but I don't want to change the question. So what I'm going to do is I'm going to divide by 4 on the outside so that they balance each other out and I'm not actually changing the question. So this is the same thing as 1 over 4 integral of 4x times 2x squared plus 1 to the power 5 over 4 dx, like so. And now this is in the perfect form. This is in the perfect form f dash of x times f of x to the power of n, which you'll be able to see on your reference sheet. This is the reverse chain rule form where the derivative of the function inside is already on the outside. And now you can just directly integrate this whole thing. And this will be 1 over 4. I'll raise this to the power of 1. So 9 over 4 divided by 9 over 4, which is 1 over 4 times 4 over 9, 2x squared plus 1, 9 over 4, which will give me 1 over 9, 2x squared plus 1 to the power of 9 over 4 plus c. So we got the exact same answer without needing to use the substitution, so it's a bit quicker. And you can do it by inspection just using the reverse chain rule like so. Okay, so this is another question. This time we're doing integration by substitution with a definite integral. So the same steps, but remember with a definite integral, we need to change our limits this time. So we start off the same way. We're going to let u be equal to our substitution. So in this case, we said u is equal to x minus 3. So our derivative of u with respect to x is going to be just 1. So therefore, we can say du is equal to dx, like that. So now, because this is a definite integral, I'm going to change my limits. So remember to do that. So actually, I'll do it here. So change limits. So my initial limits from for x were from 3 to 4. So when x is equal to 3, and I put that in, 3 minus 3 is 0. So therefore, my lower limit for u is going to be 0. And when x equals 4 here, u is equal to 4 minus 3, which is going to be 1. So my new limits are from 0 to 1. So therefore, I can say the integral from 3 to 4 of x root x minus 3 dx is equal to the integral from 0 to 1. X is, if we rearrange this, we can say that x is equal to u plus 3. If I take the 3 to the other side, x is u plus 3. So this will be u plus 3 and root x minus 3, which we said was equal to u. And dx is going to be du. So it will be equal to integral from 0 to 1. U is the same thing. Root u is the same thing as u to the power of half. So this will be 1 plus half when I multiply u with root u. So it will be u to the power of 3 over 2 plus 3 u to the power of half, like so. And now I can integrate. So this will be u to the power of 5 over 2 over 5 over 2 plus 3 times u to the power of 3 over 2 over 3 over 2 from 0 to 1. And if I take it here, it will be equal to 2 over 5 u to the power of 5 over 2 plus 3 times 2 over 3 u to the power of 3 over 2 from 0 to 1, which is going to be 2 over 5 u to the power of 5 over 2 plus 2 u to the power of 3 over 2 from 0 to 1. And when I plug in the numbers, it will be 2 over 5 plus 2 minus 0 minus 0. So therefore, my answer is going to be 2 over 5 plus 2, which works out to be 12 over 5. So therefore, that's how you would do an integration by substitution equation like that. Just remember to change your limits before you integrate. So another extension 1 area of calculus you guys learned about is how to integrate sine squared x and cos squared x. So the way we integrate them is it comes from the cosine double angle formula. So remember that cos 2x is equal to 2 cos squared x minus 1, and it can also be written as 1 minus 2 sine squared x as well. So using these results here, we can actually rearrange them so that we can say cos squared x. So just make cos squared x and sine squared x as the subject. And using this, you can actually integrate this. So when you integrate sine squared or cos squared, always remember to just change it into this form, because we can integrate these forms much easily than when it just integrated cos squared x or sine squared x. Thankfully for you guys, these results are on the reference sheet, so don't stress about if you forget them, but still a good idea to know these formulas by memory. For us, when I did the HSC back in 2018, we didn't have these formulas on the reference sheet. We had a different reference sheet, so we had to know these by heart. But for you guys, if you do forget, it is on your reference sheet. But yeah, still a good idea to sort of know these. You can just quote them because it will be more efficient that way. Okay, so in extension 1, you also learn how to do volumes of solids of revolution. So basically, a solid of revolution is the 3-dimensional solid that you get when you sort of rotate the area bounded by a curve around a particular axis. And I really love this topic here because I love the shapes that you could get with solids of revolutions. They're super cool. The idea of just rotating an area around an axis and getting a 3D shape and finding the volume of that, that's pretty cool. So the way we actually find the volume of a solid of revolution is we basically slice the volume up into a bunch of thin discs or cylinders and then basically add those slices up to get our volume. So for example, if you have this like sort of area here that you're rotating around the x-axis, when we slice, basically the radius of the slice that you get is going to be the y, whatever the y value is of that coordinate. So no matter when you move along the disk, when we or the function, when we slice, the radius of that slice is going to be y. So therefore, the area of the circle is actually going to be pi y squared. And basically, when we sum up all the disks from a to b, we actually just get an integral from a to b of pi y squared dx, because we're slicing with respect to, we're slicing, our widths of these slices are going to be delta x, a small change in x. So when we basically sum up all of these disks, we get the integral from from a to b of pi y squared dx. So that's where the formula you learned comes from. Just make sure you sort of understand that it's because the radius of this disk is whatever the y value is, and the area of the circle, we know the area of circle is pi r squared, so the area of that circle is pi y squared, because y is the radius, and therefore when we integrate these super thin disks, we will get the integral from a to b of pi y squared. And the same thing works with when you're rotating around the y-axis as well. The difference is we're slicing, our disks that we slice will look like that. So this is just a point on the graph. And instead of having the radius be the y-axis, the y value, this time the radius is actually going to be whatever the x value is. So this time, when we find the area of that circle, it will be pi x squared instead. And if this is a and this is b, we'll be integrating from a to b. And this is a small change in y, it's like delta y. So therefore, it will be dy. So yeah, basically, if you're rotating around the x-axis, this is your formula to find the volume. And if you're rotating around the y-axis, this is your formula to find the volume. So don't forget the pi, it's important. If you don't put the y, you're going to not get the right answer if you don't put a pi. Also, because this is dx and this is dy, make sure whatever you have here will be in terms of y, and this is in terms of x. So you're going to have to convert y squared in terms of x before you can actually integrate because of the dx and the dy. So here's just a question we can do. We want to find the volume of the solid formed when the area bounded by the parabola y equals 9 minus x squared, and the x-axis is rotated around, for part A, the x-axis, and for part B, the y-axis. So I reckon for the purpose of making sure we get through more content, I'm just going to do part B, but you guys can attempt part A on your own if you want an extra question to do. So always draw a diagram. We have 9 minus y equals 9 minus x squared, so that's going to be a concave down parabola. And it will actually, when y equals 0, 0 equals 9 minus x squared equals 9, so it will be plus minus 3, so we know that it has x-intercepts at 3 and negative 3. So the area bounded by this parabola and the x-axis, so this area, for part B, we are rotating it around the y-axis. So it will sort of look like this shape, where it's a dome, sort of a shape. And when we slice, we know that this point here, the radius of the slice is going to be x. So therefore, my volume here is going to be pi integral from, I'm going to be slicing from the bottom where y is equal to 0 all the way up to the top where y equals 9. So my integral from 0 to 9 of x squared dy. Now here's the thing, this is dy, so I need to make sure that this is in terms of y. We know that y is equal to 9 minus x squared, so we can say that x squared is simply going to be 9 minus y. If I rearrange that equation, I can say x squared equals 9 minus y. So this is the pi integral from 0 to 9 of 9 minus y dy. So when I integrate this, this will be pi 9y minus y squared over 2 from 0 to 9. And when I plug in the numbers there, I'll get 9 times 9, which is 81, minus 9 squared, which is 81 over 2, minus 0 plus 0. So this will give me 81 over 2 pi cubic units, like so. Remember, it's a volume, so answer with your units in cubic terms. It's cubic units. So that's what the volume is of this shape that we get when we rotate the area bounded by that parabola around the y-axis. Okay, so that's calculus. Now we can move on to vectors. So just recall what a vector is. Remember that a vector is a quantity that has both magnitude and direction. So it has two fundamental aspects to it. It has both its magnitude and its direction, and that's in contrast to what we call a scalar, which is a quantity that only has magnitude, so it doesn't have a direction. Remember that when we take the opposite vector, we mean a vector that has the same magnitude but going the opposite direction, and that the opposite vector of A is simply just going to be negative A. So if we put a negative sign in front of a vector, it will flip the direction. So if A equals AB, negative A will be BA. So it will be the same magnitude, it will just be going opposite directions. And remember, in order to add vectors together, we place them head to tail. So basically, you just put the tail of the second vector onto the head of the first vector. Then you draw the resultant vector, starting from the tail of the first vector, pointing towards the head of the second vector. So here you can see when we're adding A and B together, A plus B will look like this green vector here. And also, remember that vector addition is commutative, which means that it doesn't matter which order you add them in, you will still get the same resultant vector. So it's kind of like normal addition. We can say that 2 plus 4 is equal to 6, but that 4 plus 2 is also equal to 6. It doesn't matter which order you add them in. Same thing here. You can see what happens if I started with B instead of A. I put the tail of A onto the head of B, and I still get the same green vector that looks like that, pointing in this direction with the same length. So vector subtraction, one way you can subtract them is you can actually draw the opposite vector of the vector being subtracted, and then you can add the two together like normal. In this sense, you're treating A minus B as the same thing as A plus negative B, so the opposite vector of B. So you can see here with A minus B, I've basically drawn negative B by flipping the direction of B, and then I added them like normal, because A minus B is the same thing as A plus minus B. So I get this purple vector here for A minus B when I do that. Another way of vector subtraction is you can put the two vectors tail to tail, and then you can draw a vector from the head of the vector doing the subtracting to the head of the vector being subtracted from. So in other words, if you're doing A minus B, put the tails together, then draw a vector from the head of B pointing towards the head of A. And this order is really important. Don't draw from A to point to B. That's not going to be right. The order is important. It's kind of counterintuitive, so make sure you don't get it the wrong way around. Another way to think about it is, in order to get A minus B, we get negative B, which looks like this, plus A, like that. And when we do vector addition, it'll do that. So negative B looks like that. So negative B plus A gives you A minus B, like that. So therefore, when we have it like this, B and A, it will be a vector from the head of B to the head of A. So yeah, that order is important. So don't get it the wrong way around. And you can see both methods will work and give you the same result. So it doesn't matter which one you do. The second one's a bit faster, but if it's a bit, like if it's sort of, if you're struggling with it, you can always use this first method as well. So remember that when you multiply a vector by lambda, where lambda is any scalar, that will enlarge it by the, enlarges that vector, the magnitude of that vector by a factor of lambda. So for example, if you just have a vector A and you want to double its length, you can multiply it by 2 in order to double its length. So 2A will have twice the magnitude of A. Similarly, if you want to shrink it, you can also multiply it by sort of like a fraction in order to sort of shorten its magnitude. For example, if we want to halve A, we can just multiply it with half. And two vectors are parallel if they are scalar multiples of each other. So if b equals k times a, where k is a real number, then b is parallel to a. Because all of these vectors here are scalar multiples. And therefore they're all parallel because we can express each one as k times a, where k is just some real number. So this is question 2 from the sample NEFA Extension 1 paper. So we have a grid of equally spaced lines. The vector OH is H. So this vector we said is H. And the vector OA is A, like that. So we're asked which expression represents the vector OP. So we want to get this vector OP here. So to do that, we have to add OA to AP. So we know that OP is what we get when we add OA with AP. Now here's the thing, we know that OA is already the vector A, but here, this AC is the same thing as OH. They're both H because they're the same direction and the same length. However, AP is not the same length as OH. It's actually going to be, so if we split these into quarters, it's actually 3/4 of the length of AC. So AP is actually going to be 3/4H. So therefore, that will give us a D as our answer. So you just want to, so that assesses our knowledge of vector addition and also multiplying vectors by scalars. So in vectors, you guys also learned about component form. So when we have a vector being expressed in terms of I and j in a pair of components, that's said to be in component form. And I and j are special unit vectors where they're perpendicular and I is defined to be what a vector of magnitude 1 in the positive horizontal direction like that. And j is a special unit vector in the positive vertical direction like so. So you can express any vector as a sum of components in terms of I and j. So the vector A equals xi plus yj can also be represented as either an ordered pair or coordinates or a column vector. So you can either use your round brackets like that, or you can use the square brackets like that. I personally prefer the square rectangular brackets because this notation, we've seen it before when we did combinatorics. That's the same thing as N choose R when we did combinatorics in year 11. NCR like that. So I just like using the rectangular brackets to sort of represent it as, to really illustrate it's a vector. But of course, I think NASA in their exams, they prefer writing it like that, but it doesn't matter, you can use both. So yeah, just a summary, when we have a vector A, we're gonna, if it's, the position vector is the vector whose tail is at the origin pointing to that point. If it's a position vector, then it will be pointing to the ordered pair, which represents that same vector. But if you want to write it in component form, it will be xi plus yj, and you could also express that as a column vector. And just remember that it's only if it's a position vector that it will be pointing to the ordered pair that represents that vector. For example, I could pick this vector up and move it somewhere here, and it will be pointing at a different pair of coordinates, but those are not going to be representing that vector anymore because it's no longer a position vector. So to find vector magnitude and direction, you can use trigonometry. So basically Pythagoras, in order to find the magnitude of a vector is just square root of x squared plus y squared. And then you can also use the tan ratio in order to find the angle, the direction which is traveling in, the angle which it makes with the horizontal. And if you know the magnitude and direction of a vector, you can also resolve it into its horizontal and vertical components as well. Like, for example, if we know that this vector has a magnitude of A, if we know the magnitude of this vector A, we also can find the length of the horizontal and the length of the vertical component as well, because we know that here in this right angle triangle that cos theta is adjacent, so x over hypotenuse, which is magnitude of A. So therefore, we can rearrange that to say that x is equal to magnitude of A cos theta. And similarly, you can you can find that y is equal to magnitude of A sine theta. So this result is really useful. You do this a lot, especially when you do projectile motion, because you'll be resolving the initial velocity into its vertical and horizontal components. So now let's talk about the dot product. So the dot product is sort of like a meaningful way of multiplying two vectors together. So another word for the dot product is the scalar product. So the scalar product, the dot product is also called the scalar product because when you do the dot product, you just result in a number. It just gives you a scalar. So be careful. Don't confuse scalar product with multiplying a vector by a scalar. They're different things. The scalar product is a dot product, whereas multiplying by a scalar is just multiplying a vector with a scalar, as its name suggests, whereas the scalar product is the dot product. So, yep, the notation for the dot product is we use this little dot, hence why it's called the dot product, and it will always result in a scalar quantity, and the dot product can be calculated in two different ways. So geometrically, the dot product of two vectors is the product of their magnitudes and the cosine of the angle between them. So if we take the dot product of A and B, we can just find it. But if we have the magnitude of A and we multiply that with the magnitude of B, and then we multiply that with the cosine of the angle between those two vectors, that will give you the dot product. Algebraically, though, if you have the two vectors in component form, you can get the dot product by sort of just summing the products of each of the two vectors' corresponding components. So if you have x1i and y1j, and then you have x2i and y2j, the dot product will just be x1, x2 plus y1, y2. And you will get a scalar. You will just get a simple number when you do the dot product. And these expressions are equivalent, so they will give you the exact same thing. So both these formulas will give you the dot product. So there are some particular cases of the dot product which you need to know. Since the dot product is going to be the product of the vectors' magnitudes as well as the cosine of the angle between them, we have some special cases depending on what the angle is between them, because we know with the cosine graph, it looks like this. So this is 90 degrees, 180 degrees, 270. And 360 degrees. So basically, when theta is equal to 90 degrees, cos theta will be 0. So if this is 0, the dot product will be equal to 0. If cos 90 degrees is 0, that means if A and B are perpendicular, that means that the angle between those two vectors will be 90 degrees. And therefore the dot product will be 0. So if they're perpendicular, the dot product between A and B will be 0. And if they are going the same direction, if theta equals 0, we know cos 0 is 1. So if they're going in the same direction, cos 0 becomes 1. So it will simply just be the magnitude of the vectors together. Which means if we have the same vector dot product with itself, because the magnitude is going to be the same, so if we take the dot product of A with A, it's just going to be the magnitude of A times the magnitude of A, which is just going to be magnitude of A squared. So these two results are super important. You use them a lot in geometric proofs and any questions here in vectors. So make sure you know these results. The dot product of a vector with itself is just the magnitude of that vector squared. And the dot product of a vector, the dot product of two vectors will be 0 if those two vectors are perpendicular. And using this geometric formula for the dot product, we can actually rearrange it so that we can say cos theta is equal to the dot product of A and B divided by the magnitude of A multiplied with the magnitude of B. So that if you're asked to find what the angle is between two vectors, you can actually just use this to help you find the angle between the two vectors, just by rearranging that dot product formula. So with the dot product, it follows some rules which you need to make sure you're aware of. So we have the commutative law, so that the dot product of A and B is the same thing as the dot product of B with A. So the order doesn't matter. It's sort of like normal multiplication. 2 times 4 is equal to 8, which is equal to 4 times 2. Doesn't matter which order you do it. We also have the associative law, which basically means if we have a scalar, where k is a scalar, it can be multiplied with A first, then before you do the dot product of B, or you can just multiply it directly to the dot product of A and B, or you can just multiply it first to B before taking the dot product of that with A. It doesn't matter. You can just move around the scalar, it will still work. And then we have the distributive law, which basically says you can sort of expand brackets like how you would expand normal multiplication. So if we have the dot product of A with B plus C in brackets, that's the same thing as the dot product of A with B added with the dot product of A with C. So you can sort of expand the brackets like that. So let's just do some questions together to sort of put that into practice. So our first question is, we want to use vectors to prove the cosine rule. So we want to show that for a triangle with sides A, B, and C, that C squared equals A squared plus B squared minus 2AB cos C. So this is a different proof to another question you might be asked, which is to use the cosine rule to prove the equivalence of dot product of A, to prove the equivalence of magnitude of A multiplied with magnitude of B multiplied with cosine theta is equal to x1, x2 plus y1, y2. That's a different proof to the one we're currently doing here. But I recommend in your spare time trying to do this proof here. It's really fun. You can use the cosine rule to do that. But here we're going to do a different question. We're going to use vectors to prove the cosine rule instead. So let's just let this vector here be A, and let's just let this vector here be B. So therefore C, we can say that this vector here is going to be A minus B, like so. So now we want to use vectors to prove the cosine rule. So we're trying to show that C squared is equal to A squared plus B squared minus 2AB cos C. So C squared, the length of C here is, the length here is the magnitude of A minus B. And C squared, therefore, will be the magnitude of A minus B squared, the length of this vector squared. And the thing is, we know that with the dot product, we said that when we take the dot product of a vector with itself, we get the magnitude of that vector squared. So therefore, the magnitude of A minus B squared is simply just going to be the dot product of A minus B with itself, like so. And now we can use the distributive law to sort of expand the brackets here. So we can sort of expand the brackets like we do normally with multiplication. So this will be dot product of A with A, minus dot product of A with B, minus dot product of B with A, plus dot product of B with B. And this will give me magnitude of A squared. And here's the thing, dot product of A with B is the same thing as dot product of B with A using the commutative law. So therefore we can collect those like terms together. This dot product of B with B will simply just be magnitude of B squared. And here we'll get minus 2 times dot product of A with B. Now here's the thing, we also know the geometric definition of the dot product is going to be, we can say that dot product of A with B will simply just be A, magnitude of A times magnitude of B, times cos whatever the angle is between them. In this case, the angle between vectors A and B is just going to be capital C. So remember, magnitude of A minus B squared, we said that's equal to C squared. So magnitude of A squared, vector A squared, is just going to be A. And the magnitude of B, the vector B is just B, so B squared minus 2AB cos C. And therefore, we've proven the cosine rule, like so, just using our knowledge of the dot product. So yeah, again, this is a different question compared to if you were showing the equivalence. That is also another fun question. I recommend doing that in your own time. Okay, so here's another question. We have a semicircle APB, whose diameter is AB. So we let OA be the vector A, and then OP is the vector P, like that. So we're asked to prove that angle APB is going to be 90 degrees. So we can say that vector AP is going to be, using our knowledge of vector subtraction, so OA is, so OA is the vector A. So AP, it's a vector drawn from A pointing to P, so that's going to be P minus A, like so. That's AP. So if we can show that vector AP is, if we can show that it's perpendicular to vector BP, then we can show that this angle here will be a right angle. So we want to show that the dot product of those two vectors is equal to 0. So, but now we need to express BP in terms of P and A. So the thing is, this vector here is P, OP is P, and this vector OB is going to be the negative A because it's the same length because it's the radius of a circle, but it's going the opposite direction as OA. So therefore, BP is going to be, using vector subtraction, it's pointing to P, so it's going to be, so BP is equal to P minus OB, which is going to be minus A. So in actuality, BP is actually going to be vector P plus A. Another way you can visualize this is you can actually say that when we add vector P, when we take BO, this is also the same thing as vector A. This vector plus this vector here will be BP. So that also works too. So we know that BP is going to be P plus A. So now we know we have expressions for AP and also BP in terms of P and A. So what I can do now is I'm going to take the dot product of them. So the dot product of AP with BP is going to be the dot product of P minus A with the dot product with the vector P plus A. So now I can expand it using the distributive law of the dot product. So this will be dot product of P with P plus dot product of P with A minus dot product of A with P minus dot product of A with A. So this will be magnitude of P squared. Using the commutative law, these things are equal, so when we subtract them from each other, they'll cancel. And then the dot product of A with itself, which is going to be the magnitude of A squared. So we have these two results now. But the thing is, we notice this is a semicircle. So if we go back to our initial vectors, OA is this vector here, and OP is this vector here. But this is a semicircle, and OP is also a radius of the circle. And in a circle, the definition of a circle is all the points equidistant from the center. So all the radii, the radius should be the same as each other. So all the radii are equal. So we can say, but magnitude of P is equal to magnitude of A because radii of the same circle are equal. So therefore, if that's equal to each other, therefore this thing is equal to 0. Because if the lengths are equal, when we square them together and subtract them from each other, they're still going to be 0. So therefore, we can say that AP is perpendicular to vector BP, and therefore angle APB is 90 degrees, like so. So for part B, they're asked what circle geometry theorem have we proven? Basically, P is just any point here. It's basically saying in this it's basically saying that in the semicircle, so here this is 90 degrees, APB. But P could have been any point on the semicircle. It could have been here or here. Basically, no matter what you do, you're going to get right angles. So if you recall, if you ever did circle geometry in junior school, like in year 7 to 10, you'll know that in a semicircle, the angle subtended at the circumference by the diameter will be a right angle. So that's basically the circle geometry theorem we've just proven, which is really cool, using vectors to do that. So in vectors, you guys also learned about projections. So when a vector is broken into a pair of components, we already know that that's rewritten as a projection of the vector onto the x and y axis. So for example, when we have this blue vector, xi, yj, xi is the projection of A onto the x-axis and yj is the projection of A onto the y-axis. However, we don't always need to necessarily project vectors onto the horizontal or vertical axis. You can actually just project them onto any other vector we want. So for example, here we can project this blue vector onto this black vector here, and our projection will be this red vector. So the way to visualize a projection is sort of just think of the projection as sort of the shadow of the vector. So for example, just imagine you're shining a torch on the vector. The shadow here is the projection of this vector onto the other vector. And the way we notate the projection of A onto B is we have projection of A onto B like that, with B in subscript like so. So the formula we use to find the vector projection is if we have a vector and we're projecting onto here, if this is the angle between, so this is B and this is A, the length here we know is going to be magnitude of A cos theta using trigonometry. So that will counter for the length. But in order to get the direction, to make sure it's not just a length that's going anywhere, like it could be the same length, but it could be going in any direction. In order to make sure that it's going in the same direction as B, we're going to multiply it with the unit vector of B. So that is in the same direction as B, but with a magnitude of this result here. However, this formula is a pure formula. It's the one where a projection formula comes from. But it's not always the easiest to plug numbers into this formula because you might not always know the angle between the vectors. So using some manipulation, we could also get these other results, which you might, this one is the most common one, which you will be definitely using at school. And it comes from the dot product. We know that the dot product of A and B is magnitude of A and B multiplied together times the angle between them. So therefore, we can rearrange and we can say that magnitude of A times cos theta is equal to the dot product of A and B divided by magnitude of B. So if we plug that into this form here, our projection of A onto B will simply just be, this will become dot product of A and B over magnitude of B. And we know that the unit vector of B we get by dividing B with its own magnitude. So therefore, this thing will become dot product of A and B, magnitude of B squared times B, like that. And the magnitude of B squared is just going to be the dot product of B with itself, like so. And that's how we get this formula, which you'll see at school. Comes from this pure formula, but just with the dot product rearranged to make it into an easier form to use. So here's sort of a standard E1, E2 level question you might be asked in an exam. what is the vector projection of A onto B? So remember that projection of, so basically, here we got -1, -2, so this is A, and -4, -3. So yeah, so we're basically finding this projection here onto B. So projection of A onto B, we said, is dot product of A with B over dot product of B with itself times the vector B. So here, dot product of A with B is going to be -1 times -4 plus -2 times -3. And dot product of B with itself is -4 squared plus -3 squared. And that's all multiplied with -4i minus 3j. So this will give us, will be 4 plus 6 over 16 plus 9. Yeah, 4 plus, so -4i minus 3j. So this will be 10 over 25, which is 2 over 5. -4i minus 3j. And this will give us -8 over 5i minus 6 over 5j. And that is your vector projection of A onto B. So if we have time, I have extra questions here on the slides, but I'm just looking at the time and we do have a lot of content still. So I'm just going to give this question to you guys as a bonus question for you to do for extra practice doing vectors. So you can practice doing more questions on vectors. So on that note, we can move on to another topic now, which is statistical analysis. So just recall from the Maths Advanced course, you guys learned about random variables. So we talked about how they are variables whose possible values are outcomes of a statistical experiment or a random phenomenon. So random variables are useful because they allow us to basically study random processes by quantifying their outcomes. So just remember that random variables are notated using capital letters and their values are represented by the corresponding lowercase letter. So for example, you might use the capital letter X to define, to be the random variable that we can define to be the number of heads that you throw, that you've got, the number of heads that you receive after you toss a coin 10 times. So in that case, with this notation, probability that the probability that capital X equals X is a probability of throwing X number of heads, whereas if you do X equals 4, that's a probability of throwing exactly 4 heads, but if you have X is greater or equal to 4, that's a probability of throwing at least 4 heads. So yeah, that's just a bit of notation. With random variables, we use capital letters to notate them. And you also learned about, in Maths Advanced, the expected value or the mean, which is a measure of central tendency. And we learned that we notate mean using the Greek letter mu, and that to find the mean, we sum all the outcomes multiplied with the probability of them occurring together to give you the weighted average for the mean. You also learned about variance, which is a measure of spread, and variance is the expected value of the squared deviation of a random variable from its mean. So basically what you're doing is you're taking every value, you're subtracting it from the mean, then you're squaring that, and then you're calculating the average of that to get your variance. So that's reflected here. You're subtracting all the values from the mean, you're squaring them, then you're taking the average of that. This is the formal definition of variance, whereas, however, it's not always the easiest to use. So in Maths Advanced, you guys learned how to you use this alternate formula, which gives you the same result, and it's easier to use. So you just take the expected value of x squared, and then you subtract it from the mean squared. And you also learn about standard deviation, which is the measure of spread using the same units as the original random variable. Remember here in variance, we had to square the deviances, which is what you get when you subtract the number from the mean. But in order to sort of compare it with the same units as the original variable, you want to, because we squared it, we need to go back, we need to reverse what we did, so we will square root it. So when you square root the variance, you'll get the standard deviation. So you guys also learned about the difference between discrete and continuous random variables. So a random variable is discrete if its values can be listed or counted. So for example, if you're looking at like the number of heads that you get after you throw a coin 3 times, that is discrete because you can literally count and list all of those values. For example, you can have 0 heads, 1 head, 2 heads, and 3 heads. You can count them. So they're discrete values because you can sort of list them and count them. However, a random variable will be continuous if its values can take any value along a continuum. So for example, you might have the height of students in a classroom, because you could be 171 centimeters. You could also be 165.72 centimeters or 1.8 to 167 meters. Like, you just have all these values you can take on a continuum. So therefore it's continuous because there's like infinite amount of values along a continuum. Of course, if you did say height to the nearest centimeter, for example, then it will become discrete because you'll be like 179 centimeters, 180 centimeters, 178 centimeters. It will become discrete if you round it. If you say height to the nearest centimeters, but if you just say height without specifying that it's rounded, then it will be continuous because it will be on that continuum. So that's all Maths Advanced content. It's important to have that in the background, but we are also interested in the Extension 1 specific material. So in Extension 1 Maths, we're concerned about a special kind of discrete random variable, which we call the Bernoulli random variable. And instead of having a bunch of outcomes, the Bernoulli random variable only has 2 possible values it can take. It's either 0 or 1. And 0 represents failure and 1 represents success. So there's only 2 outcomes of a Bernoulli trial. So yeah, as I mentioned already, Bernoulli random variables are used in these things called Bernoulli trials, and they're experiments where there's only 2 possible outcomes, where we label them either failure or success. And we define P, the letter P, as our probability of success. So since there are only 2 possible outcomes of a Bernoulli trial, the probability of failure is therefore going to be 1 minus P, because there are only 2 outcomes, and the sum of all the outcomes the probabilities of all the outcomes should give us 1. So the probability of failure is just therefore going to be 1 minus P. And of course, we're talking about success and failure here, but you want to note that success doesn't necessarily have to be something good. For example, it could be just a manufactured toy having a defect, for example. It's just the specific situation where you have 2 outcomes, and that outcome happening is what we call success. So it doesn't need to be something positive. It could be something bad, actually, but we still call it success. So a Bernoulli random variable has a probability distribution called a Bernoulli distribution that looks like this. So remember, a Bernoulli random variable only has 2 outcomes, 0 and 1. So the probability of success is P, so therefore the probability of failure is 1 minus P. And therefore we can calculate the mean and the standard deviation. So remember that the mean is the sum of all the outcomes multiplied with the probabilities of it occurring. So here the mean of the Bernoulli distribution is going to be 0 times the probability of it occurring plus 1 times the probability of it occurring. So 0 plus 1 times P, which is P, so therefore that will be P. And in order to calculate the variance, we will say that, remember, variance is going to be equal to the expected value of x squared minus the mean squared. So to find the expected value of x squared, we're going to square the values and multiply it with the probability of it occurring. So we got 0 squared times 1 minus p plus 1 squared times p minus the mean squared, which we said was p. So here we got 0 plus 1 squared p. So this is p minus p squared. So this is the same thing as p times 1 minus p. So yeah, we said that expected value is p and variance is p times 1 minus p. So of course, to get the standard deviation, then you just square root it. So those are Bernoulli trials. This is the Bernoulli distribution. If we repeat Bernoulli trials over and over again, we will end up getting something called a binomial experiment. So a binomial random variable represents the number of successes of getting in n independent Bernoulli trials. So how many successes did you get after you did n Bernoulli trials? And the way we notate a binomial random variable in a binomial experiment with n number of trials and a probability of success p is x with this squiggly symbol, we call it tilde, b standing for binomial, n for number of trials, and p for probability of success. You might also see this written as bin for binomial. So I think on a reference sheet they use that notation. But yeah, that just basically just says x is binomially distributed with n number of trials and p as a probability of success in each trial. So when we want to find the probability of having exactly r successes in n trials, we use this formula here for binomial probability, where we do n choose r times p to the power of r times 1 minus p to the power of n minus r. So the reason why this formula works is this n choose r accounts for how many ways we could get r successes out of n trials. So remember, think back to year 11 when we did combinatorics. Out of n trials, we want to choose r of them to be successes. How many ways can we do that? How many combinations can we get? We have n choose r number of those, the ways we could get r successes out of n trials. Then we want specifically r successes, so the probability of getting success is p. So if we do that r number of times, it'll be p times p times p, so it'll be p to the power of r. But we also want to have n minus r number of failures. So the probability of that occurring is 1 minus p. So 1 minus p times 1 minus p, etc. So we'll get 1 minus p to the power of n minus r. So for example, we're asked if we play 30 rounds of air hockey with our friend David, and the probability of you winning a game is 2/30. What is the probability that you win 2 out of the 30 rounds? Well, in each round, there's only 2 outcomes. You either win the air hockey round or you lose the air hockey round. So therefore, each round of air hockey, it can be considered a Bernoulli trial because there's only 2 outcomes. And therefore, the number of wins you have is the random variable x, where x is binomially distributed with 30 number of Bernoulli trials and the probability of success in each trial being 2/30. So if you want to win 2 out of the 30 games, to win exactly 2 times, you need to win twice and lose once. In order to win twice and lose once, we have 2 rounds of winning. So each round of winning is 2/30. So 2/30 times 2/30. So that's 2/30 squared. And you also need to have lose once. So losing, the probability of that is 1/30. However, you also need to account for how many ways this can occur, how many combinations of like winning twice and then losing once. You can win the first 2 and then lose. You can also win, then lose, then win, or you can lose, then win, then win. And to account for that, we do 30 choose 2, which gives us 30, which will account for all of these ways we can win twice, then lose once. So therefore, your probability that x is equal to 2 is going to be 30 choose 2 times 2/30 squared times 1/30, which will give you 4/9. So your probability that you win exactly 2 out of the 30 rounds is going to be 4/9. So I want you to take a moment. You can pause this lecture here and sort of think about whether or not you can use binomial probability in each of the following scenarios. So I'll let you guys think about that. And think carefully. Okay, so remember we talked about finding the expected value and variance of the Bernoulli distribution earlier on. So the Bernoulli distribution is a special type of binomial distribution because there's only one Bernoulli trial being held. So if we repeat Bernoulli trials over and over again for a binomial experiment, if we have n Bernoulli trials, therefore we can also find the variance and the expected value of the binomial distribution. So if there's n trials and each Bernoulli trial has an expected value of p, then overall in n Bernoulli trials, our expected value should be np. And since each Bernoulli trial is independent of each other, the variance of the sum of trials, which is the binomial experiment, because that's where we have all those trials together, is going to be equal to the sum of each individual trial's variance. So therefore, after you have n Bernoulli trials, we have np 1 minus p as our variance for the binomial experiment. So in other words, we just put a p in, we put an n in front of each of these terms, and then that will give us our expected value and variance of the binomial distribution. And apologize if this seems to be rushing a bit. It's because we are pressed on time. We need to get there within those 2 hours of the lecture. So, but yeah, basically this is really important. This is on your reference sheet. Make sure you know this. If you have a binomial random variable x, the expected value is going to be np, and your variance is going to be np times 1 minus p. Really important. So here's a question. If x is a random variable whose distribution is defined as such, for part A, we're asked find the mean and standard deviation of the distribution. For part B, how many more trials would be needed to increase the mean to 100? And for part C, what effect does this have on the standard deviation and distribution? So for part A, we're asked to find the mean and standard deviation of the distribution. Remember, the mean is going to be np. So that's going to be this 150 trials. So here n is 150 and p is 2 over 5. So 150 times 2 over 5 will give us our expected value. So in this distribution, our expected value is going to be 60. And our variance is going to be np times 1 minus p, which is going to be 150 times 2 over 5. Oh wait, I've given myself extra space here. So again, I've already found here on the previous slide that mean is 60. And standard deviation is, variance is going to be np times 1 minus p. So this will be 150 times 2 over 5 times 3 over 5, which will give me 36. So the variance is 36, so therefore the standard deviation is going to be the square root of that, so it's 6. So therefore we know that the mean of this distribution is 60 and our standard deviation is going to be 6. So for part B, we're asked how many more trials would be needed to increase the mean to 100. So let's say we know that P is still, the trials will still have the same probability of success. So if we do n times 2 over 5, where n is some unknown number of trials, we want the mean to be 100, because we know the mean is np. So therefore, n would be 100 divided by 2 over 5, which will give us 250. But we need to read the question carefully. We can't just answer with 250. They're asking how many more trials would be needed. So we already have 150 trials already. So therefore, we will answer 100 more trials are needed. Because we already have 150 trials, we want 250 in total. So after 100 more trials, you will get a mean of 100. So they're asking in part C, what effect does this have on the standard deviation and distribution? So we can say when n is equal to 250, what will the standard deviation be? Well, the variance will be equal to n times, so it will be 2, oops, dropped my pen. It will be equal to n times p times 1 minus p, which is 250 times 2 over 5 times 3 over 5, which will give us that will give us 60. And when we take the square root of 60, that is going to be 7.75 to 2 decimal places. So we can see that this is bigger than our initial standard deviation of 6. It's a larger number. So when they ask what effect does this have on the distribution, we can say that because the standard deviation is bigger, the distribution is wider. Everything is going to be more spread out. So if we increase the number of trials, the standard deviation will increase and the spread will be wider. So in extension 1, in this course, you also learned about the sample proportion. So the sample proportion, instead of writing the number of successes we get, the sample proportion is just the proportion of the proportion of successes that you have over the total number of trials that you ran. So in other words, we use this little p with a hat to represent the sample proportion. It's just the number of successes you got as a proportion of the total number of trials you did. So the sample proportion gives us an estimate of the probability of success p. So you can work out the expected value of the sample proportion and the standard deviation of the sample proportion simply just by dividing your expected value and your standard deviation by n. So in other words, if x is binomially distributed with n number of trials and a success probability of success p, then your expected value is np, your variance is npq, where q is equal to 1 minus p, and your standard deviation is root npq. So therefore, for the sample proportion, you can just divide expected value with n to get p, and your standard deviation with n as well to get that result. Which means we can work out the variance by squaring the standard deviation, which will give you pq over n. So yeah, that's a really cool result. The expected value of the sample proportion is p, which makes sense because it's supposed to be an estimate of your probability of success. So your expected value of what the sample proportion should be is your actual p, and then your standard deviation is root npq over n. So you also learned how to approximate the sample proportion using the normal distribution. So recall from Maths Advanced that the normal distribution is a special type of continuous probability distribution with a bell curve shape. So if we have a random variable x which is normally distributed with a mean of mu and a variance of sigma squared, then we can notate it like so. So the first letter here is going to be the mean, the second letter is the second number is going to be the variance. So the standard normal distribution is a normal distribution which has a mean of 0 and a variance or standard deviation of 1. So it's a common practice to use z instead of x for the standard normal random variable. And from Maths Advanced, the probability density function of the standard normal distribution, we can notate it using this, we use this Greek symbol phi. So this function is representing this probability density function of the standard normal distribution. And the area under the curve will give you probability, remember? So the probability that that z is less than or equal to x is the order area or to the left of that. And the area can be represented using the cumulative distribution function. So that will represent the area under the curve, or from the left all the way up to the x. And we use the capital letter phi to represent that cumulative distribution function. So basically what I'm saying is, if I say, like, I don't know, if I plug in 0.5 into this cumulative distribution function of the standard normal distribution, that basically tells me the area underneath the probability density function all the way up to 0.5. So whenever you use the standard normal table, you need to, because this is, the standard normal table will only give you results for the standard normal distribution. So if you're working with any other distribution, you need to standardize it using z-scores. So from Maths Advanced, you learned that to standardize, you just take that, take your value, take your score, you subtract it from the mean, then you divide it by the standard deviation. So let's just do this question now to sort of illustrate all of that in action. And apologies again for the rush. We are already running over time, so we're just going to quickly finish off this question now. So here we're told in a recent census that 20% of the adults in a city eat out regularly. And for part 1, we have a survey of 100 adults in the city is to be conducted to find the proportion of those who eat out regularly. Show that the mean and standard deviation for the distribution of sample proportions of such surveys are 0.2 and 0.04 respectively. So here, you either eat out or you don't eat out, so there's 2 outcomes. We have 100 adults surveyed, and from the census, we know that the actual probability of success of them eating out regularly is 0.2, so 20%. And it's binomially distributed because there's 2 outcomes. So, but this is a survey, and we're trying to see we're trying to find a mean and standard deviation of the distribution of the sample proportions of the surveys. So remember that for the mean of the sample proportion, that's going to be NP divided by N, which is just P, which is just going to be 0.2. And they want us to find the standard deviations of the sample proportion. So the standard deviation of the sample proportion is going to be root NPQ divided by N, which is going to be root 100 times 0.2 times 0.8 divided by 100. So that's going to be times 0.2 times 0.8. That's root 16 over 100, which is 4 over 100, which is 0.04. So therefore, we've shown that the mean and standard deviation of the sample proportions is 0.2 and 0.4 respectively, as required. So that's just relatively straightforward. You just need to make sure you remember that to find the standard deviation and mean of the sample proportion, you just take your normal standard deviation and your normal mean and divide it by the number of by the number of people that you have, or the number of trials that you had. So in this case, we had 100 as our value for n. So that is part I, part 1. So for part 2, they're like use the extract shown from the table, giving values of p where z is less than z. So this is the z table for the standard normal distribution, and this will all give you the area underneath. This is the values of the cumulative distribution function, giving you the area under the probability density function of the standard normal distribution. So we want to estimate the probability that a survey of 100 adults will find at most 15 of those surveyed eat out regularly. So that means we're trying to find the probability that Z So we're trying to find a probability that x is less than or equal to 15, which is equal to the probability that for your sample proportion, that is going to be less than or equal to 15 over 100. Because we surveyed 100 people, so our sample proportion, we want it to be less than 15 over 100. So we're trying to estimate the probability using this table. Remember, this is just a normal approximation. Remember, this is discrete data here, but we are approximating it using the standard deviation. I mean, we're using the normal distribution to approximate it instead. So that's approximately going to be the same thing as the probability that z is less than or equal to. So this is 15 divided by 100 is 0.15. So we're going to standardize it. So 0.15 minus our mean. We said the mean was 0.2. And our standard deviation is 0.04. So that's approximately the probability that z is less than or equal to, when we do 0.15 minus 0.2 divided by 0.04, that will be negative 1.25. So here we don't, so this is negative 1.25, but we don't have 1.25 here. We have positive 1.25 here, which is 0.8944. But remember, the normal distribution is symmetrical. So basically you're saying, so if this is negative 1.25 and this is positive 1.25, the area to the left of 1.25 is the same as the area to the right of 1.25. So what this table gives us here for 1.25 is all the area to the left of 1.25 here. So to find this area here, we can just subtract this area that we got here from the table from 1, because the area under the entire curve should be 1 under the probability density function of the standard normal distribution. So therefore, this will be equal to 1 minus our value we got here, 0.8944. Which is going to be 0.1056. So therefore, you have around a 11% chance that at most 15 people will eat out regularly if you survey 100 adults. So yeah, that's how you do it. You kind of want to be creative with your distribution as well, with your normal distribution. So yeah, we are over time, but I do have some important maths tips for you guys. And obviously we didn't have enough time to go through all of the calculus topic and also the trig topic as well. But I do have all of these tips for you guys, which you do have access to because you have access to my slides. So I recommend going through the slides that I have and making sure you go over these tips, because I've listed them here for you. I would like to go through them ideally if we had time, but unfortunately we don't. So we're just going to have to, you're just going to have to browse through the tips on the slides, but they are there for you. And these are common mistakes that I see come up a lot. So make sure you don't make those mistakes and just be super careful with them. So yeah, for example, in this induction question, if you're substituting n equals k plus 1 into this thing, don't do 2 to the power of 2k plus 1 plus 6. That's wrong. You want to do 2 to the power of 2 times k plus 1 plus 6. You want to substitute it into brackets when you're doing substitutions like that. And I also have some mnemonics here for you to help you memorize your trig results. And obviously SOHCAHTOA. Also be careful when you're doing trig questions with domains, and make sure you check your blind spots with the T formula to make sure you don't miss a solution. Also, yeah, don't forget your plus C with indefinite integrals. Don't forget your pi in front of the integral sign when you're doing volumes of slows of revolution. And For projectile motion, always derive the equations from scratch unless they are given to you in the question. And yeah, stuff like that. And some final exam tips for you guys. Make sure when you're in the exam room, don't rush too much. Like, stay calm, because quality control is good, but quality assurance is better. So if you don't do business studies, that might be a bit confusing. But basically what I'm saying is fixing mistakes by double checking is good. So by fixing it reactively by double checking, that's a good idea. Make sure to double check your answers. But isn't it even better to just get the question right the first time and not have any silly mistakes along the way? So be proactive with your quality control. So just make sure it's better to just get it right the first time. So just take your time, read it carefully, read the question carefully, don't make silly mistakes. And if you rush too much, you're going to accidentally, like, I don't know, miss a minus sign, and then it'll be so annoying to lose marks for dumb things like that. Also, write big and write neatly. You don't want to annoy your markers or lose marks, because they're the ones reading your paper. If you make it too hard to read, make sure your writing is legible. Otherwise, they're going to get annoyed, or you might accidentally make a mistake. For example, if you write too like that, it might be too confusing. So I like to write I put a line through the Z to make sure that it is, you can see it's a Z. And yeah, make sure your graphs are decent size. Make sure that at least a third of a page big, so you can put all the detail you have on them. And attempt every question, because you miss 100% of the shots you don't take. So even if you don't know how to do the question, see if there's a previous part of the question you can use to apply in a later part to try to scrape as many marks as you can. Also, remember to keep writing. Don't get bogged down by a question, because otherwise it will impact the rest of your paper. So if you find a hard question, just try to do it, but don't get stuck and frozen on it for a minute if you don't know how to do it. Especially if it's a harder one, like a projectile motion or a vector geometric proof question. Worst case scenario, just skip it, then come back to it later, because you want to make sure you have time to do the other parts of the paper. Yeah, again, be super wary about silly mistakes. Be super careful, and make sure you don't make silly mistakes like forgetting minus signs, or like forgetting the plus C with indefinite integrals. Show all your working. Don't skip steps, be comprehensive. You're allowed to use English words, English sentences to sort of explain what you're doing. Yeah, you don't want to omit too many steps. You want to be clear about how you did your working. So yeah, that's all from me. Thanks so much for watching this lecture. Remember to stay calm in the exam room. Good luck for trials. I wish you guys all the best. And yeah, enjoy the rest of your July holidays. Thanks so much for watching. And yeah, all the best for trials and also your HSC and the rest of your studies. Thanks so much.